Hello everyone, welcome to Basics e-learning.
In lesson number 4 video, Z-transforms, I am going to discuss initial value theorem and final value theorem. The first 3 lectures where I have discussed what is a Z-transform, how to apply a Z-transform and the important properties of Z-transform, and also I have discussed what is an ROC and properties of ROC in the previous lectures. So the link of which I am going to leave in the description box. Not only Z-transform, introduction to signals and systems, I have released 15 lectures in my YouTube channel, for which I am going to leave a link in the description box. Please check it out. As discussed in the earlier videos, x of z, that is the Z transform, can be applied only on the discrete time signals, that is x of n. So for every x of n, there exists a Z transformed signal. The corresponding Z transformed signal, here I am representing it as x of z. By definition, x of z is defined like this. Sigma n is running from minus infinity to infinity. X of n, z power minus n. As I am telling, x of n is a discrete signal. Let us take x of n is equal to different instants. Values are 5, 3, 0, 2, 1. Something I am taking like this. Suppose say my n is equal to 0 is like this. So this is n is equal to minus 1, 1, 2, 3. That is, this is a both-sided signal. So if I want to apply x of z, that is, if you want to find out x of z for this x of n, this is simply the range now is limited to minus 1 to 3. Instead of taking minus infinity to infinity, now n is minus 1 to 3, x of n, z power minus n, right? So now if you write it, apply n is equal to minus 1, that is I am just expanding the summation, then it will be x of minus 1, z power minus of minus 1 plus 1 plus x of 0, z power 0 plus x of 1, z power 1, right? So minus 1 plus x of 2, z power minus 2 plus x of 3, z power minus 3. This is how we can apply, or we can find out Z transform of any given x of n. So now substitute, see this is x of minus 1, x of 0, x of 1, x of 2, x of 3. So if I write, this is 5z plus 3, z power 0 is 1, right? So plus 1, 0, right? X of 1 is 0, so this is 0, plus 2z power minus 2 plus 1 into z power minus 3. So this is nothing but 5z plus 3 plus 2z power minus 2 plus z power minus 3, right? So this is how I am finding my x of z. So suppose if you are given with x of z and you want to find out x of n, that is called applying inverse Z transform, right? So to find out x of z from the given x of n, you need to apply Z transform, whereas the reverse, from the given Z transformed signal to find out the discrete time signal, you need to apply inverse Z transform. Suppose say here this signal x of n can have the range from n is minus infinity to infinity. Anywhere the signal may exist. Now suppose if you want to find out x of 0 or x of infinity, right? So this initial value theorem and final value theorems are used to find out x of 0 and x of infinity directly using formula. Otherwise, how do you need to find out? See here, after finding, suppose say if you are given with x of z, apply inverse Z transform, get x of n. X of n you will be getting in the form of an equation. So there you substitute n is equal to 0 once. Then you will get x of 0 value. Similarly, substitute n is equal to infinity. Then you will get x of infinity, right? So that is the procedure. So using initial value and final value theorems without doing this complex calculation, means that is converting the x of z into time domain using inverse Z transform, then putting n is equal to 0 and n is equal to infinity. So this complex calculation is avoided by using directly the initial value theorem and final value theorem. Right? Now I will explain how these initial value and final value theorems are derived. First, I'll explain initial value theorem. Before applying initial value theorem or final value theorem on the problem, any of the given problem, one should remember that the signal x of n has to be causal. Then only you can apply this initial and final value theorem. So, initial and final value theorems are defined only for causal sequences. Remember. So, for causal sequence, the signal exists only from n greater than or equal to 0. That is, n is running from only 0 to infinity. Now, let us see how this initial value theorem is defined. So, for any causal sequence x of n, the initial value theorem is defined like this. X of 0 is equal to limit z tends to infinity x of z. Now, I'll explain you the proof. So, how this is derived. Let us see. So, as you know, x of z is equal to sigma n is running from minus infinity to infinity x of n z power minus n. Right. Now, as I am telling, x of n is a causal sequence. The limit here, the summation changes from sigma n is running from 0 to infinity x of n z power minus n. Understood, right? Here n is existing only from 0 to infinity. Minus infinity to 0, that part it is 0, right? So, this is your causal sequence. Causal means it exists only for n greater than 0. N greater than or equal to 0. Right. Now, I am expanding my summation here. See, x of 0, z power minus 0 plus x of 1, z power minus 1. Right. Plus x of 2, z power minus 2. So on. Right. Now, this is nothing but here x of 0. Z power 0 is 1. Right. Now, plus x of 1 z power minus 1 plus x of 2 z power minus 2 plus so on. Now, I am applying limit z tends to infinity on both the sides. Limit z tends to infinity, apply it on both the sides. So, limit z tends to infinity x of z here on my left hand side, that is equal to x of 0. It doesn't have any z term here, right? So, that is coming as it is. Plus, see here, x of 1 z power minus 1 is nothing but x of 1 into 1 by z can I write? So, 1 by infinity, that is 0 plus 0 plus 0. So, any of the other terms will be getting 0 only. See here, this is nothing but the definition here, right? X of 0 is defined as limit z tends to infinity x of z. So, the derivation of this initial value theorem is very simple. Just follow the steps here what I have explained, very simple. Final value theorem is defined as x of infinity is equal to limit z tends to 1 z minus 1 into x of z. So, let us see how this is defined. So, we know the definition x of z is sigma n is running from minus infinity to infinity x of n z power minus n, right? This is nothing but z transform of x of n, right? So, now suppose say if we want to find out z transform of x of n plus 1 minus x of n, right? That is, in place of x of n, I have this much that I am going to write here. So, sigma n is running from minus infinity to infinity x of n plus 1 minus x of n z power minus n, right? Now, the signal is a causal sequence. So, I am taking the signal is from 0 to infinity x of n plus 1 minus x of n z power minus n. Now, apply z tends to 1, that is limit z tends to 1 on both the sides. So, limit z tends to 1, z transform of x of n plus 1 minus x of n here is defined. So, here z, if you are keeping 1 power anything is 1 only. So, my right hand side is more simplified. Sigma n is running from 0 to infinity x of n plus 1 minus x of n, right? Now, I'll expand. If you put n is equal to 0, I'll get x of 0, 0 plus 1, right? So, x of 1 minus x of 0, first term, plus next put n is equal to 1, that will be x of 2 minus x of 1. Now put n is equal to 2, right? So x of 3 minus x of 2. So the summation will go on like this. Now what happens, see here, x of 1 will get cancelled, x of 2 will get cancelled, so x of 3, like this it will get cancelled, only that x of infinity term will be left. So for this summation, if I expand the summation and cancel out, what I am getting here is, that is here on my left hand side, sigma z tends to 1, Z transform of x of n plus 1 minus x of n here is defined here as minus x of 0 plus x of infinity. By linearity theorem, we know here, see, Z transform of x of n plus 1 minus x of n can be also written as Z transform of x of n plus 1 minus Z transform of x of n. Right. So now, what is Z transform of x of n plus 1? I know for Z transform of x of n is, that is direct formula, x of z only, right? So, my left hand side will be minus x of 0 plus x of infinity. But we don't know what is this Z transform of x of n plus 1. So, there is a formula for Z transform of x of n plus m. It is defined, it's a big formula. There is no need to remember this formula. Directly you can write it down. Only for your explanation purpose I am writing. So the formula is defined right like this. Z bar m x of z minus sigma k is running from 0 to m minus 1 x of k z bar minus k. So here this is x of n plus 1, that is in place of m I have to write 1 in the formula. So this will be z bar 1, right? X of z minus sigma k is running from 0, m minus 1, 0 minus 0 is 0. So the summation won't come into picture here. So x of k z bar minus k. So this is only applied, this summation is existing only for k is equal to 0 here, right? So upper limit, lower limit both are zeros only. So k is equal to 0 I am writing. So x of 0, z bar 0 is 1 here. So z transform of x of n plus 1 is defined as z multiplied by x of z minus x of 0, right? So now you write down this here, right? I am just replacing here. This is nothing but z into x of z minus x of 0. Now we can simplify this one to get the value of x of infinity, right? So this is the equation that I am getting. So let us simplify this equation to get the value of x of infinity. As you have here, my left hand side is limit z tends to 1, right? So here also you can take that limit z tends to 1 on your right hand side also. So if I expand this, simplify, minus x of 0 plus x of infinity here is given by limit z tends to 1 z into x of z minus x of 0 minus x of z here. So this side also I have that limit z tends to 1, right? So x of 0 will get cancelled on both the sides. So what I am getting is x of infinity is equal to limit z tends to 1 here. So these two terms you take z minus 1 common, x of z is the remaining. So x of infinity is defined like this by final value theorem. So without finding the inverse z transform of the given signal x of z, you can find out the final value of the causal signal x of infinity using this final value theorem.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.